April 15, 1895, Chicago and Northwestern Railroad Construction Camp, Nebraska. The engineering calculations from Yale-trained railroad specialists would never fully capture what they witnessed that spring morning. American construction crews operating steam shovels that defied everything Eastern engineering wisdom said was necessary for large-scale earth-moving projects. Through the prairie dust and mechanical thunder of the Nebraska worksite, 20-year-old Otis steam shovels moved earth with efficiency that seemed impossible to engineering school graduates. No precision roller bearings, no advanced metallurgy, no $8,000 price tags per machine. Yet they moved more dirt per day than the latest Marion Model 40 steam shovels that Eastern firms insisted were essential. In modern engineering offices, technical specialists required the newest machinery to handle railroad construction. Each project demanded cutting-edge equipment, complex mechanisms, factory-trained repair technicians, specialized replacement parts. Most carried costs that consumed entire construction budgets. The prairie crews were operating with construction philosophy the Eastern engineers had never imagined profitable: proven durability, field repairable components, equipment that local blacksmiths could maintain, daily productivity that reduced costs from thousands to hundreds per cubic yard moved. 400 miles from Eastern engineering schools, the most decisive construction revolution in American railroad history was revealing itself. Not in superior technology, not in precision manufacturing, but in the systematic understanding that connected every Irish and German immigrant worker with machinery they could actually fix. The morning sun cast long shadows across the Nebraska prairie as Tom Mackenzie stood beside the Chicago and Northwestern surveying stakes, studying the engineering reports that would determine his financial future. 400 miles of railroad track needed cutting through soil so dense that Eastern firms claimed only the most advanced machinery could handle the volume. 1 million cubic yards of earth had to move in 18 months, and the men in pressed suits from Chicago had made their position abundantly clear. William Bradford adjusted his wire-rimmed spectacles and spread the technical specifications across a makeshift table fashioned from railroad ties. The Yale-educated engineer's leather portfolio contained detailed analyses of every steam shovel manufacturer from Ohio to Pennsylvania, each recommendation backed by mathematical precision that reflected his formal training. The Marion Model 40 represents the pinnacle of earth-moving technology, Bradford announced, his voice carrying the authority of academic credentials. 4 cubic yards per scoop cycle, steam pressure rated at 150 pounds per square inch, roller bearing assemblies engineered for maximum operational efficiency. Mackenzie ran weathered fingers along the cost projections, his Irish accent thickening with skepticism. $8,000 per machine, and you're telling me we need 5 of them to meet deadline. He had spent 30 years building America's railroads, learning machinery through bitter experience in remote camps where equipment failures meant men died and fortunes disappeared. The mathematics troubled him more than Bradford's confident predictions. James Morrison, the railroad's president, studied both men from beneath his expensive bowler hat. Corporate investors in Chicago expected modern solutions to engineering challenges, and Morrison's reputation depended on delivering results that satisfied board members who measured success through quarterly reports. Mackenzie, the engineering consultants are unanimous. These Marion shovels represent proven technology. We cannot afford to experiment with this project's timeline. The Irish contractor walked the survey line, calculating volumes through methods learned in Pennsylvania coal camps and Michigan timber operations. His boot heels marked distances, while his experienced eye estimated soil density through subtle changes in prairie grass patterns. When Mackenzie spoke again, his words carried weight earned through decades of successful projects completed under impossible conditions. I can move your 1 million cubic yards for less than half that investment. 3 machines instead of 5. $1,800 instead of $40,000. Bradford's pen stopped moving across his calculation sheets. What equipment are you proposing that costs $600 per unit? No reputable manufacturer produces steam shovels at such prices. Mackenzie's weathered face revealed the slight smile of a man who had solved problems through practical wisdom rather than theoretical knowledge. 1875 Otis steam shovels, 2 cubic yard capacity, 120-pound steam pressure, 22 tons operating weight. I know where 3 are available from completed Pennsylvania projects. The Yale engineer's professional composure cracked slightly. Those machines are antiques, 20 years old, designed before modern metallurgy standards. They'll break down constantly under prairie conditions. Bradford's logbook contained detailed reliability studies proving that equipment older than 5 years represented unacceptable risk factors for large construction projects. Morrison felt the familiar tension between conservative engineering wisdom and Mackenzie's unorthodox approaches that had delivered profitable results on previous contracts. The railroad president understood corporate politics well enough to know that backing obsolete equipment could destroy his career if the project failed catastrophically. Explain your reasoning, Mackenzie. How do 3 old machines outperform 5 new ones? The construction veteran's mathematics proved devastatingly simple. 3 shovels moving 2 yards each equals 6 cubic yards per cycle. 1 Marion moving 4 yards equals 4 cubic yards per cycle. My way moves 50% more dirt per operational sequence. Mackenzie's hands sketched operational diagrams in the prairie dust, illustrating cycle times that reflected real-world conditions rather than manufacturer specifications. Bradford consulted his engineering tables, searching for flaws in Mackenzie's logic through systematic analysis that had served him well in academic settings. You're ignoring operational efficiency factors. Modern roller bearings reduce friction losses. Advanced boiler designs maximize steam utilization. Precision manufacturing ensures consistent performance parameters. The Irish contractor had heard similar arguments from engineering graduates who confused theoretical perfection with practical reliability. I inspected a broken 1893 Marion at a Kansas job site last month. Complex roller bearings seized after 2 years. Local mechanic told me those bearings need factory-trained repair technicians. Takes 6 weeks to get replacement parts from Ohio. Mackenzie's voice carried the authority of a man who had watched expensive machinery fail in remote locations where downtime destroyed project schedules. Morrison studied the cost projections again, recognizing the financial implications that could determine corporate profitability. $40,000 for new equipment versus $1,800 for used machinery represented savings that would impress Chicago investors, but operational failure would cost far more than initial purchase prices. What guarantee can you provide that 20-year-old equipment will maintain operational reliability? Mackenzie pointed toward the surveying stakes that marked 400 miles of construction challenges. Those Otis machines have simple chain hoist mechanisms that any blacksmith can repair. Horizontal boiler design that field crews understand completely. Basic components that don't require specialized knowledge or factory replacement parts. His confidence reflected 30 years of successful projects completed through practical engineering rather than theoretical sophistication. Bradford closed his leather portfolio with deliberate precision, recognizing that his carefully researched recommendations faced challenge from experience-based alternatives he had not considered. The young engineer's formal training had prepared him for technical calculations, but not for decision-making scenarios where practical wisdom contradicted established engineering principles. The Nebraska wind carried dust across the prairie as 3 men contemplated choices that would determine whether American railroad construction embraced proven innovation or expensive tradition. The first Otis steam shovel arrived at the Nebraska construction camp on a flatbed railroad car that groaned under 22 tons of cast iron and steel forged in the industrial furnaces of 1875. America. Patrick O'Brien circled the machine like a master craftsman examining raw materials, his calloused hands tracing boiler seams and testing chain tension with the systematic precision of a man who understood that mechanical failures in remote locations killed workers and destroyed reputations. The Pennsylvania coal mines had taught him to read machinery through touch and sound, interpreting vibrations and steam pressure fluctuations that engineering school graduates never learned to recognize. Mackenzie supervised the unloading process, while Bradford documented every visible defect in his leather-bound logbook, recording rust patterns and wear indicators that supported his conviction that obsolete equipment represented unacceptable risk factors. The Yale-educated engineer measured boilerplate thickness with precise calipers, noting metallurgy standards that predated modern manufacturing specifications by 2 decades. "This machine shows clear signs of structural fatigue," Bradford announced, his voice carrying professional authority backed by technical measurement. "The boiler pressure gauge indicates previous operation beyond safe parameters." O'Brien knelt beside the horizontal boiler assembly, examining riveted seams with the practiced eye of a mechanic who had maintained steam equipment through Pennsylvania winters that froze lubricants solid and cracked inferior metals. His toolkit contained instruments crafted over 20 years of field repairs, specialized wrenches, and measuring devices that no factory had ever manufactured. "The boiler's been maintained properly," O'Brien declared, running experienced fingers along welded patches that revealed careful repair work. "These Otis machines were built when foundries used iron thick enough to last 50 years. The second and third shovels arrived within the week, each machine representing different operational histories that O'Brien analyzed through systematic inspection procedures developed during coal mine employment, where equipment failure meant cave-ins and worker deaths. The lead engineer documented boiler pressure capabilities, engine timing specifications, and track gauge measurements that would determine operational efficiency on Nebraska's challenging prairie soil. Mackenzie's crew of Irish and German immigrants assembled around each machine, their industrial experience spanning coal mines, steel foundries, and railroad construction projects where improvised repairs meant survival. Bradford established a documentation system that recorded every maintenance requirement, operational delay, and repair cost associated with the antique equipment. His methodical approach reflected engineering school training that emphasized systematic data collection as the foundation for reliable performance analysis. "These machines require daily maintenance procedures," Bradford noted, watching O'Brien adjust steam pressure valves that newer equipment automated through precision manufacturing. "Modern Marion shovels are engineered for operational reliability that minimizes manual intervention." O'Brien's preparation routine demonstrated the systematic approach that had kept Pennsylvania mining equipment operational through conditions that destroyed lesser machinery. Each morning began with boiler pressure testing at 140 pounds per square inch, 20% above normal operating requirements to ensure safety margins that protected crew members from steam explosion hazards. Engine timing calibration followed precise procedures that maximized fuel efficiency, while maintaining power output sufficient for prairie soil conditions that varied between hard clay and sandy loam, depending on seasonal moisture content. The chain tensioning process required mechanical intuition that O'Brien had developed through years of field experience with hoisting mechanisms that lifted tons of coal and rock through mine shafts where failure meant catastrophic accidents. Each link received individual inspection, with worn components replaced using locally sourced materials that matched original specifications through careful metallurgical analysis. Track gauge adjustment demanded understanding of soil compression rates and machine weight distribution that engineering textbooks described theoretically but practical experience taught through trial and error. Bradford's resistance intensified as O'Brien's modifications demonstrated capabilities that contradicted established engineering wisdom about obsolete equipment limitations. The Yale graduate documented every repair procedure, noting that field modifications voided manufacturer warranties and created liability issues that corporate management would find unacceptable. "You're essentially rebuilding these machines using untested engineering principles," Bradford observed, watching O'Brien strengthen bucket supports with steel plates obtained from local blacksmith shops. The Irish mechanic's innovations reflected understanding that machinery designed for Pennsylvania coal mines required adaptation for Nebraska railroad construction, where soil conditions and operational requirements differed significantly from original design parameters. Custom modifications included improved steam flow systems created through simple pipe reconfiguration that increased operational efficiency by 15% without compromising safety standards. Track extensions fashioned from local materials allowed operation in soft prairie soil that would bog down heavier machinery, while standardized repair procedures using commonly available components ensured that remote location breakdowns could be resolved without factory technician assistance. Mackenzie watched his crew transform 20-year-old equipment into precision earth-moving tools that reflected American mechanical ingenuity rather than European theoretical engineering. The construction veteran recognized that O'Brien's systematic approach combined practical experience with innovative problem-solving methods that no engineering school curriculum could teach. Each machine represented investment recovery potential that exceeded new equipment capabilities while maintaining operational flexibility essential for remote construction projects. Morrison arrived for inspection as O'Brien completed final preparations that transformed obsolete mining equipment into railroad construction machinery optimized for Nebraska conditions. The railroad president studied operational readiness indicators that would determine corporate investment success or failure, recognizing that his career reputation depended on results that satisfied Chicago board members who measured performance through quarterly profit reports. Bradford's documentation provided technical evidence supporting concerns about antique equipment reliability, while Mackenzie's confidence reflected 30 years of successful projects completed through practical engineering wisdom that challenged established industry practices. The morning prairie wind carried coal smoke from 3 steam shovels ready to prove that American mechanical innovation could outperform expensive European engineering tradition through systematic preparation and experienced operation. The breakthrough came on a sweltering June morning when Sean Murphy operated the lead Otis shovel through a cycle time that defied every engineering prediction Bradford had calculated. The Irish immigrant's hands moved across steam controls with practiced precision, coordinating boiler pressure, track movement, and bucket positioning through timing sequences that reflected 5 years of railroad construction experience. Each scoop lifted exactly 2 cubic yards of Nebraska clay, swung through a perfect arc, and deposited earth onto waiting rail cars with mechanical rhythm that never varied despite prairie heat that reached 95 degrees by noon. O'Brien recorded operational statistics that transformed Mackenzie's theoretical calculations into documented reality. 300 cubic yards moved daily per machine, achieved through operational efficiency rather than raw mechanical power. The simplified control systems allowed operators to complete dig cycles in 45 seconds compared to 60-second averages recorded on new Marion equipment at competing job sites. Field repairable components eliminated the downtime that plagued complex machinery requiring specialized technician assistance for routine maintenance procedures. Bradford consulted his logbooks with growing bewilderment as daily productivity reports contradicted every engineering principle he had learned through formal academic training. The Yale graduate's measurements showed Mackenzie's 3 antique shovels consistently moving 900 cubic yards combined, while reports from Kansas indicated that single new Marion Model 40s averaged 350 cubic yards under similar soil conditions. These numbers violate basic mechanical efficiency calculations, Bradford muttered, checking his mathematics against manufacturer specifications that promise superior performance from advanced engineering. The operational advantages extended beyond simple productivity measurements into maintenance reliability that proved decisive for remote construction projects. Mackenzie's crew achieved 94% operational availability through O'Brien's systematic maintenance routine that prevented breakdowns rather than responding to equipment failures. Each morning began with boiler inspection, chain lubrication, and pressure testing that identified potential problems before they caused costly downtime. Compare this to reports from competing projects where new Marion shovels averaged 73% availability due to complex mechanical systems that required factory-trained repair specialists. Murphy's mechanical intuition allowed him to coax maximum performance from temperamental steam equipment through understanding that transcended formal training. The young Irishman could predict boiler pressure fluctuations by listening to steam valve sounds, adjust engine timing by feeling vibration patterns through operator platform floors, and detect bearing wear through subtle changes in mechanical rhythm that engineering instruments never measured. His ability to maintain consistent productivity while preventing equipment damage represented skills that no technical school curriculum could teach. O'Brien's field modifications proved impossible to implement on precision-manufactured equipment designed for factory-controlled environments. The master mechanic strengthened bucket supports using locally sourced steel plates that matched original metallurgy through careful analysis, improved steam flow with simple pipe reconfigurations that increased efficiency 15%, and created custom track extensions that prevented soft soil problems plaguing heavier machinery. These innovations reflected American mechanical ingenuity that adapted existing technology to specific operational requirements rather than accepting manufacturer limitations. Daily repair costs averaged $23 per machine for Mackenzie's operation, compared to $67 reported from projects using new Marion equipment. The difference reflected O'Brien's standardized repair procedures using materials available from local suppliers rather than specialized components that required weeks for delivery from Ohio factories. When chain links wore thin, Murphy's crew replaced them with standard hardware store items that O'Brien modified to match original specifications. When steam lines leaked, field welding using common materials restored operational capability within hours rather than waiting for factory technicians. Worker productivity measurements revealed advantages that escaped Bradford's engineering calculations but proved decisive for project economics. Mackenzie's crews averaged 15 cubic yards moved per man-hour through operational systems that utilized immigrant workers' industrial experience rather than requiring specialized training for complex equipment. The simplified controls allowed operators to focus on soil conditions and loading efficiency rather than managing intricate mechanical systems that demanded constant technical attention. Morrison arrived for monthly inspection as summer heat tested equipment reliability under conditions that separated proven machinery from experimental technology. The railroad president studied productivity reports that exceeded corporate projections by margins that impressed Chicago investors while maintaining operational costs below budget projections. Mackenzie's approach had delivered measurable results that validated practical engineering wisdom over theoretical innovation, though Morrison recognized that corporate credibility required continued performance through seasonal challenges that would test equipment durability. Bradford's resistance evolved from technical skepticism toward grudging recognition that field results contradicted academic predictions about obsolete equipment limitations. The young engineer's systematic documentation revealed productivity advantages that defied engineering school assumptions about machinery performance curves and operational efficiency factors. His leather logbook contained daily measurements proving that 20-year-old equipment outperformed modern alternatives through systematic maintenance and experienced operation rather than advanced manufacturing technology. The Irish and German immigrant crews developed operational pride that reflected successful mastery of challenging mechanical systems through practical knowledge rather than formal technical training. Each man understood his machine's individual characteristics, recognizing steam pressure sounds that indicated optimal performance, identifying vibration patterns that warned of developing problems, and executing maintenance procedures that prevented failures before they occurred. This operational intimacy created efficiency levels that no engineering manual could specify or factory training program could duplicate. By August's end, Mackenzie led construction schedule by 6 weeks, while operating 40% under budget through equipment costs that railroad executives had initially considered risky experimentation. The 3 antique steam shovels had moved over 50,000 cubic yards of Nebraska prairie soil with reliability that proved American mechanical wisdom could triumph over expensive European engineering tradition through systematic understanding of proven technology rather than pursuit of theoretical innovation. The approaching autumn would test whether summer success could survive seasonal challenges that historically destroyed construction schedules and equipment reliability across the harsh American frontier. The first, killing frost, arrived in late September, coating the Nebraska prairie with ice crystals that transformed summer's productive construction site into a mechanical proving ground where equipment survived or failed based on fundamental design principles rather than manufacturer promises. Temperatures dropped to 20 below zero by November, creating conditions that exposed every weakness in complex machinery, while revealing the advantages of simple engineering that had sustained American industry through decades of frontier challenges. O'Brien's morning inspection routine adapted to winter realities that tested equipment reliability through environmental stresses no factory testing program could duplicate. The horizontal boiler design of the Otis shovels maintained consistent steam pressure despite brutal cold that caused advanced multi-stage systems to lose efficiency through condensation problems and pressure fluctuations. Cast iron components handled temperature stress cycles that cracked newer alloy materials engineered for theoretical performance rather than seasonal durability. Manual control systems remained functional when hydraulic mechanisms froze solid in conditions that rendered precision equipment inoperable. Murphy wrapped his hands around steam valve handles that stayed warm through direct heat transfer from boiler systems, while reports from competing job sites described operators struggling with frozen controls on new Marion shovels that isolated mechanical systems from heat sources through advanced engineering designs. The young Irishman could maintain operational timing despite wearing heavy winter clothing because simple lever mechanisms required basic physical manipulation rather than precise finger coordination that complex control systems demanded. Bradford documented the winter performance differential with measurements that challenged every assumption about modern equipment superiority. His logbook recorded operational temperatures where Mackenzie's antique shovels continued productive work while new machinery shut down completely. At 15 below zero, the Otis machines maintained 80% normal productivity through basic mechanical systems that functioned regardless of environmental conditions. Reports from Kansas indicated that Marion shovels ceased operation entirely when temperatures dropped below zero due to precision bearings that seized in cold weather. The fuel efficiency advantages became pronounced as winter increased coal costs from $12 per ton to $36 per ton, due to transportation difficulties that affected all remote construction projects. O'Brien's simple steam systems burned 15% less fuel than complex multi-stage boilers that lost thermal efficiency through intricate pipe networks designed for maximum power rather than fuel conservation. The horizontal design allowed more complete coal combustion through longer flame travel paths that extracted maximum energy from expensive fuel supplies. January's blizzard tested equipment durability through conditions that separated proven mechanical design from theoretical engineering innovation. 3 weeks of continuous snow and wind created operational challenges that revealed fundamental differences between machinery designed for controlled factory environments and equipment engineered for American frontier conditions. When the storm cleared, Mackenzie's shovels resumed operation immediately through starting procedures that required only basic coal, water, and manual ignition systems. The competing Marion shovel suffered catastrophic failure during restart attempts that exposed design vulnerabilities masked during normal operation. Precision bearings had seized during the extended shutdown period, requiring complete disassembly and replacement with factory components that took 2 weeks to arrive from Ohio. The complex steam regulation system needed recalibration by trained technicians who charged premium rates for winter travel to remote locations. Bradford calculated that the advanced shovel required 14 days and $800 in repairs to restore operational capability. O'Brien's systematic approach to winter maintenance demonstrated practical engineering wisdom that no academic training could provide. Each evening, shutdown followed procedures that protected equipment from freezing damage through techniques learned during Pennsylvania coal mine employment where overnight temperatures regularly dropped below zero. Steam lines received alcohol treatment that prevented ice formation. Mechanical bearings got additional lubrication that maintained flexibility despite temperature extremes. And boiler systems remained partially heated through controlled combustion that prevented thermal shock damage. The operational availability statistics proved devastating to arguments about modern equipment reliability. Mackenzie's 3 shovels maintained 87% winter availability through systematic maintenance and simple mechanical systems that functioned reliably regardless of environmental conditions. The single Marion achieved 31% availability due to complex mechanisms that required specialized repair procedures and factory replacement parts unavailable during prairie winters. Worker morale remained high among Mackenzie's crews, who appreciated equipment they could understand and repair through practical skills rather than specialized training that left them helpless when machinery failed. The Irish and German immigrants took professional pride in mastering mechanical systems that responded to intelligent operation and systematic maintenance rather than requiring factory technician assistance for routine problems. Murphy's ability to diagnose equipment condition through sound and vibration gave him confidence that no complex monitoring system could provide. Morrison reviewed winter performance reports that exceeded corporate expectations despite seasonal challenges that typically destroyed construction schedules and profit projections. The railroad president recognized that Mackenzie's approach had delivered measurable advantages that proved practical engineering wisdom could triumph over expensive theoretical innovation through systematic understanding of proven technology rather than pursuit of manufacturing novelty. Corporate investors in Chicago expressed satisfaction with results that exceeded budget projections while maintaining construction timeline despite brutal winter conditions. Bradford's transformation from skeptic to grudging advocate reflected the power of documented evidence over academic prejudice. The Yale engineers' systematic measurements proved that simple, well-maintained machinery outperformed complex alternatives through reliability factors that engineering school curriculum never emphasized. His logbook contained daily statistics demonstrating that 20-year-old equipment achieved superior performance through operational characteristics that theoretical analysis had never predicted. February's thaw revealed the decisive nature of winter testing that separated equipment designed for American conditions from machinery engineered for European theoretical standards. Mackenzie's lead in both schedule and budget had increased through seasonal challenges that typically favored expensive equipment with advanced engineering support. The 3 antique steam shovels had proven that American mechanical wisdom could deliver superior results through systematic maintenance and experienced operation rather than complex manufacturing technology designed for controlled environments. The approaching spring would bring new challenges that would test whether winter success represented fundamental equipment superiority or seasonal advantage that might disappear under different operational conditions. The catastrophic failure occurred at precisely 7:43 on the morning of March 15th, when 20 years of accumulated metallurgical stress combined with spring thaw conditions to create the disaster that Mackenzie had spent his entire career trying to prevent. Sean Murphy had completed his routine pressure check and found the boiler gauge reading 125 pounds per square inch, well within normal operating parameters for the lead Otis shovel that had performed flawlessly through Nebraska's brutal winter. The explosion that followed lasted 3 seconds and destroyed everything Mackenzie had built over the previous 10 months. The steam blast threw Murphy's body 30 feet from the operator platform. His life ended instantly by superheated vapor that reached temperatures exceeding 400 degrees Fahrenheit. 2 German immigrants working nearby suffered severe burns as metal fragments and scalding steam created a killing zone that extended 50 yards from the demolished boiler assembly. The machine that had moved over 60,000 cubic yards of prairie soil became twisted wreckage that testified to the unpredictable nature of aged pressure vessels operating under frontier conditions. O'Brien reached the accident scene within minutes, his experienced eyes immediately recognizing the distinctive pattern of catastrophic boiler failure that had killed Pennsylvania coal miners throughout his 20-year career maintaining steam equipment. The master mechanic's systematic inspection revealed the truth that federal investigators would later confirm through metallurgical analysis. The explosion originated from a boiler patch installed during previous employment, where inexperienced repair work had created a weak point that gradually deteriorated under operational stress until spring temperature fluctuations caused final structural failure. Bradford arrived as O'Brien documented evidence that would determine whether the accident represented fundamental design flaws or maintenance negligence that could have been prevented through proper engineering oversight. The Yale graduate's technical analysis focused on metallurgical factors that academic training had taught him to recognize, noting that iron forged in 1875 lacked alloy compositions that modern manufacturing used to ensure pressure vessel reliability. His preliminary report emphasized that 20-year-old equipment operated beyond acceptable safety margins regardless of maintenance quality. Federal railroad safety inspectors descended on the construction site within 48 hours, their investigation driven by regulatory requirements that held corporate management personally liable for worker deaths caused by equipment negligence. Inspector General William Hayes had spent 15 years investigating industrial accidents across the American frontier, developing expertise in distinguishing between unavoidable mechanical failures and preventable disasters caused by cost-cutting measures that sacrificed worker safety for profit margins. Mackenzie faced the darkest crisis of his construction career as news of Murphy's death spread through Irish immigrant communities that supplied railroad labor throughout the Midwest. The victim's widow, Margaret Murphy, arrived with 3 children under age 10, seeking explanations for a tragedy that had destroyed their family's economic future. The construction veteran who had built his reputation on worker safety found himself confronting the human cost of decisions that had seemed prudent when measured against corporate profit requirements and construction deadlines. Morrison received telegraphed reports from Chicago executives who demanded immediate explanations for accidents that could trigger federal investigations and corporate liability lawsuits worth hundreds of thousands of dollars. The railroad president understood that his career depended on demonstrating responsible corporate behavior that prioritized worker safety over cost savings, regardless of previous performance advantages that McKenzie's approach had delivered. Corporate lawyers advised immediate termination of all contracts using obsolete equipment to minimize legal exposure from potential wrongful death claims. The Irish construction crews who had worked alongside Murphy for 5 years questioned McKenzie's judgment for the first time since the project began. These men had trusted their lives to equipment that their contractor assured them was safer than expensive alternatives, and Murphy's death shattered confidence that had sustained morale through brutal winter conditions and dangerous working environments. Productivity dropped 40% within a week as operators approached steam shovels with fear that replaced the operational confidence essential for efficient earth-moving work. Bradford's detailed investigation revealed the systematic maintenance failures that had created conditions for catastrophic boiler failure, despite O'Brien's careful attention to routine operational requirements. The damaged boiler showed evidence of multiple repairs using inferior materials and inexperienced welding techniques from previous job sites where proper engineering oversight had been unavailable. These accumulated weaknesses had created a pressure vessel that appeared sound during normal inspection, but contained structural flaws that guaranteed eventual failure under operational stress. O'Brien's professional reputation suffered devastating damage as fellow mechanics questioned his competence to maintain steam equipment safely despite his 20 years of successful experience with similar machinery. The master mechanic's systematic approach had prevented dozens of potential accidents through careful attention to mechanical details, but Murphy's death overshadowed every successful repair and maintenance procedure that had kept workers safe during hundreds of operational hours. His confidence in field maintenance capabilities crumbled under evidence that some equipment problems exceeded the scope of practical repair methods. Hayes completed his federal investigation with findings that devastated McKenzie's claims about equipment reliability and systematic maintenance procedures. The Inspector General's report documented metallurgical evidence proving that the failed boiler had operated with structural weaknesses that made catastrophic failure inevitable, regardless of operational care or routine inspection procedures. Federal regulations required immediate shutdown of all steam equipment older than 15 years, unless certified through expensive engineering analysis that most contractors could not afford. The moral weight of Murphy's death transformed McKenzie from confident innovator to haunted contractor who questioned every decision that had led to tragedy that could have been prevented through acceptance of conventional engineering wisdom. The 3 children who would grow up without their father represented consequences that extended far beyond corporate profit margins or construction schedules. Margaret Murphy's tears reminded McKenzie that his pursuit of cost efficiency had extracted human prices that no financial savings could justify. Morrison arrived for emergency consultation as corporate pressure mounted to terminate McKenzie's contract and replace obsolete equipment with new Marion shovels that carried manufacturer warranties and federal safety certifications. The railroad president faced difficult choices between loyalty to a contractor whose innovations had delivered exceptional results and corporate responsibility to prevent additional worker deaths that could destroy company credibility and trigger massive legal liability.